these are the things that this unit's about. The biggest part about getting over some of the speed bumps here is that we're going to be dealing with some really, really large or really, really small numbers. And I have found that some students need a little bit of a refresher on scientific notation in order to be successful. Part of the reason is because Newton's law of universal gravitation is something that's relatively straightforward to see, but has some interesting values in it. For example, we're going to be talking about a gravitational constant in a few minutes, big G, not to be confused with little g. You should remember in your notes what little g is. We used it to represent the acceleration of gravity near the surface of the Earth. It is not universal. In fact, put that in your notes. When we say Newton's laws of universal gravitation, we mean it's the same everywhere in the universe. That's why the word universal is used here, not because they own a theme park or make movies. We're saying it because we believe this rule is the same everywhere. So when we observe other stars or supernova or galaxies, we apply this rule to describing what's happening there. The acceleration of gravity, that lowercase g, was just something that was near the surface of the Earth. And even then, it's not the same everywhere near the surface of the Earth. It changes. As you go up into the mountains, or if you're near an oil deposit, or you're near the a water reserve, g changes, it fluctuates. Big G, however, is an actual universal constant, one that we're going to be talking about. In fact, it's the universal constant related to Newton's law of universal gravitation. So let's start right with, and go back to Newton's law of universal gravitation. It's kind of bizarre. Newton had his hand in lots of areas of physics. We think of it just in Newton's laws, but gravity, optics, sound, he believed that he wrote the definitive works on all versions of everything that's studied in physics. Not necessarily was all of it great. This one is a little interesting in that he kind of pulled it out of nowhere. He has reasons why he believed the law would work this way, but he had no way of verifying it. This is Newton's law of universal gravitation. So to understand what it's about is it tells you the force of gravity between any two things in the universe. So any two things. So perhaps you and a friend. If you and your friend are somewhere in the universe, this law will tell you the size of the force of attraction acting on you. Gravity is a force of attraction. It pulls things together. Newton's law of universal gravitation allows you to find the force between any two objects at once. Now, I want to be careful. There are thousands of objects in my room, and there is a force of gravity between all of them. This law only allows you to take into account two things at once. If you want to have a third friend somewhere else, well, suddenly there's lots of forces now to worry about. This law only takes them two at a time. Please put that in your notes. Because the moment I put a third thing in there, people do weird stuff like adding M3 and R. They just do weird things. This law only works on two things at once. So if I want to find out this force, I have to take these two things into account. But if I want to find out this force, I have to take these two things into account. And I have to take them into account separately. The three-body problem. For our class, just about everything will be just two-body problems, like that. Now, each piece I think is obvious. M1 is the mass of the first object. M2, mass of the second object. R represents the center-to-center separation distance between the two objects. G is the universal gravitational constant. This is a true fundamental constant in that it is something that is the same everywhere in the universe. Again, it's called the universal gravitational constant. It's on your equation sheet. You should find it. But more importantly, understand that you won't have to memorize it. It will be given to you. It's kind of a weird number and hasn't changed much since it was discovered and measured by Cavendish back about 350 to 400 years ago. It's just really not easy to measure. It's 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. It's got complex units, but it has to. Look at the law real quick. I've got kilograms squared in the numerator and meters squared in the denominator, but I have to be left with newtons. All universal constants are scaling values. They scale your value for the units you're using. This is the version of the universal gravitational constant that's in meters, newtons, and kilograms. There's a different version that's in pounds and feet. Now, to get to the point here, I want to take a brief aside, and this involves you using your calculator for a minute. So please take your calculator out. And if you could, please, find that on your calculator. I'm under the impression you guys are aware of scientific notation. But my experience is that you're not particularly great at dealing with it. If you found this button, then you know that it's actually not a button on its own. It is a part of another button. Please don't use this for scientific notation unless you are actually meaning to use it. What does this button actually do? What does it calculate? The logarithm, that's right. If I asked you what a logarithm was, could you tell me? Lance said yes. So Lance, what's the logarithm?
It's when you want to find like something, what something to a certain power equals.
David?
It's the inverse of an exponential.
Okay. It's not the inverse of an exponential. Exponential refers specifically to e. So the natural log is related to the inverse of the exponential. So, but these are different. This would be the base 10. This is the base e log. You guys learned these things, right? The different bases. All right. The logarithm produces an exponent. That's what the function does. It tells you the exponent that you would have to put to 10 that would give you the number in question. Most people don't fully appreciate that logarithms, like if I say I have the log of x, that this on its own is an exponent. It's just the exponent part. I'm saying all this because I have students in the room right now who, when they see this, want to use this. You need to stop right now. Don't. This is a function in your calculator. It performs a function. If you use this, you're going to start getting your answers wrong because we have to not only have large numbers. For example, we'll be talking about the Earth, 5.97 times 10 to the 24th kilograms. And its radius, 6.37 times 10 to the 6 meters. And you're going to have to do all sorts of work with them, like square them and multiply them by other numbers. And don't forget, 6.67 times 10 to the negative 11th newtons meter squared per kilogram squared. You start putting all that into your calculator and you start using this number, it's all going to be screwed up. So find this. Find your EE button. For most of you, it's above the comma. You find it okay? When you want to type in a number that has scientific notation as a part of it, you type in the root number, then for almost all of you, it's going to be second, and then the comma, and then the rest of the number, the part that's the exponent. Don't hit the log here to use 10 to the x. Don't do it. Use the EE button. The calculator will treat this as a single number, not as a function. If you put it in there as a function, you'll have order of operation problems, and your numbers will always be off by powers of 10. So please use this. In fact, to remind you, I will write all scientific notation as an E, just like this, to try and dissuade you from using that. Does everybody understand? We're going to practice right now. We're going to go back to our example here, and we'll use some relatively common numbers here. I'm going to say person 1 is 70 kilograms. That's about 140 pounds. Person 2, we'll say is 60 kilograms, about 120 pounds. And they're separated by 3 meters. I would like you to tell me the force of gravity between them. Not particularly hard to do. It's also going to help you understand why we tend to not feel these forces. But you're going to use this expression to calculate the force of gravity. I don't believe I have to put all this together for you, but I may. So the first person, 70 kilograms. Second person, 60 kilograms. Their separation distance, 3 meters. Don't forget that that's squared. Times 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared.
Only the plus.
Yeah, 3.11 times 10 to the negative 8th newtons is the correct answer. Most of you got this answer. A few of you made some subtle mistakes. An over-reliance on this button can sometimes screw you up. Unless you understand what that button is doing on your calculator, you may find that it's doing a different calculation than you're intending. So be careful with that button. That's on the TI models, right? You guys will have the answer button. It takes whatever the last thing in there and does something to it. There tends to be an over-reliance on it, so be careful. This answer's in newtons because kilograms canceled out to kilograms, and the meter squared canceled out to meter squared, leaves you in newtons. Look, a 60 kilogram person would weigh 600 newtons, and a 70 kilogram person would weigh 700 newtons. That's the force between the person and the earth. You understand that there's no way you feel this force, right? It's tiny. This is why we don't feel these interactions with other things that are around us. And you can get as close as you want to a person. You can never get to zero. People don't overlap, and neither do objects. That's why it's always the center to center distance. So now that you've done that, we're going to maybe practice something a little bit bigger. Let's take one of you and put you on the earth. Now, I don't care which person in the room we deal with here, so why don't you all try it? There's 2.2 pounds per kilogram. So you know how much you weigh. Find out what your mass is in kilograms. I want you to use U. The Earth has a radius of 6.37 times 10 to the 6th meters, and the Earth has a mass of 5.97 times 10 to the 24th kilograms. Yeah, it's big. I'd like you to find the force of gravity between you and the Earth. But I want you to use Newton's law of universal gravitation to do so. Which would be the mass of the Earth, the mass of you, divided by your separation distance. We'll assume the separation distance is the radius. Right? I don't think I have to add the extra meter for how tall you are. Is that okay? You see that it won't really matter? So I'm not going to worry about that. And don't forget G there. So please take a minute and do this. Again, if I instead just dropped you near the surface of the Earth, you'd be accelerating. It would be the force of gravity that would be accelerating you. If I wanted to find out what that acceleration was, just divide out by your mass. And this is how you know if you're doing it right. Now, I don't think I have to do this, but anybody not getting 9.8? Because if you don't get 9.8, you're doing it all wrong. And that's why we need to practice for this acceleration. So if you're trying to find the acceleration of gravity on another planet, you take that force of gravity and you set it equal to ma. But you divide out the object that you're putting on the planet. In this case, it was you. What that leaves you with is an acceleration of gravity. Notice I'm not using lowercase g specifically. I'm saying the acceleration of gravity. This could be for any planet. If I give you the radius of Mars and the mass of Mars, this is how you could calculate the acceleration of gravity near the surface of Mars. And it'll be the mass of that planet times g divided by the radius of that planet squared. This is how you calculate the acceleration of gravity on other planets. Now, we tend to, have to find other ways then to figure out what these things are. But acceleration of gravity on the moon is about 1/6 of the Earth. On Mars, it's about 60% of the Earth. But this is how you would calculate it directly. Now, I do want, this whole stuff about the gravitational force today. So I'm going to try and draw a picture of what you guys just saw. So here's my attempt. All right, so you guys would agree that the stopper is traveling like this around in a circle? All right. And I drew the string in, and I drew the little thing in the center there that I was holding, the little handle here. But it was traveling around in that circle. This distance represents something we call the radius of curvature. I know it sounds like I'm making a big deal about the word radius, but for whatever reason, the moment I add of curvature, people tend to think it's a new word. It's still just the radius of this circle. But the radius of curvature doesn't have to be a complete circle. If you are traveling down Sheldon and you make a left turn onto Linebaugh, your car changes direction. It travels in a curved path through the intersection. That curved path has a radius of curvature, even though it's not a complete circle. So you understand now what I mean by a radius of curvature? It just represents the radius of the curve you're traveling along. So you don't have to travel in a complete circle to have a radius of curvature. You just have to change direction. And any change in direction will have a radius of curvature. Any change in direction will have a radius of curvature. I don't want to say that 4 times. Is twice enough, or do you want me to go a 3rd time? Any change in direction will have a radius of curvature. Now, the whole time the object was spinning in the circle, there was tension acting on the stopper, this direction. But at the instant, in the freeze frame of this particular example, the object had a velocity in this direction. We call this the tangential velocity. With a little t next to it to indicate that the velocity was tangent to the path. And we call the tension here a radial force because it's towards or along a radius. Now, this tension causes the object to change direction. I'm trying to be really cautious of my words here, but it causes the object to change direction. So that after a few minutes, the object is now, say, over here. The string's still attached, so we still know we have tension this way, which means the force has now changed direction. The force is now pointing towards the center, still. But the object's velocity has changed. Now the object has a velocity in this direction. The speed doesn't have to change here, but the direction is changing. Now, you should understand something, that you can change speed and change direction at the same time. There's no reason why you can't. Many of you see the yellow light and decide that it's at that moment you must make the left turn. So you increase your car's speed so that you can make the intersection. And then once out there, immediately find yourself going too fast, so you slam on the brakes and turn the wheel at the same time. I followed you guys. I see how you drive. And this is what many of you do. Well, your car's slowing down and changing direction at the same time, no big deal. Of course, assuming your car can do that and not slide out of control. That's why if you look at the opposing curb, you'll see all sorts of black all over it from everybody who did not make the turn correctly and ran into the curb. But let's assume that you successfully make the turn. You can have two different kinds of accelerations at the same time. You can have an acceleration that changes the size of your speed, and you can have an acceleration that changes the direction of your velocity. I'll say that again. You can have two different accelerations at the same time. You can have an acceleration that changes the size of your speed, and you can have an acceleration that changes the direction of your velocity. I'm using my words carefully here. So you can have two different accelerations at the same time. You can have an acceleration that changes the size of your speed, makes you speed up or slow down. Or you can have an acceleration that changes your direction, the direction of your velocity. In this picture, if I want to change the size of the speed, I would need a tangential acceleration. That'd be an acceleration either this way or this way. It has to be in the direction the object is traveling to speed it up or slow it down. So an acceleration that is in the direction of your velocity will speed you up or slow you down. This is what we've been used to so far this year. However, if I merely want to change direction, I have to have an acceleration that is radial, an acceleration that is perpendicular to my velocity. There's a lot of descriptors here, and I want you to have them all. If I want to change an object's direction, then I have to have an acceleration that is perpendicular to the velocity. It has to be radial or along a radius. Now, this is the crux. This is the important part. This acceleration has no component in the direction of motion. So it can't speed you up or slow you down. It can only change direction. A center-pointing acceleration can only change direction. We have a name for this kind of acceleration. It's called a centripetal acceleration. This is an acceleration where the speed doesn't change, but the velocity changes direction. I will write it not with it's radial, so we say that it's along a radius, but when I describe it, I put an A with a little c here to remind me that this is not something where that's speeding up or slowing down. This is something that's changing direction. Now, so far this year, if I've wanted to calculate how a tangential acceleration works, well, I just find how much the velocity changes and divide by the time. This was a motion equation. That's what we've been doing all year when it comes to dealing with accelerations. But this won't work because the object's speed isn't changing. So if you want to calculate a centripetal acceleration, meaning how much acceleration does it require to make a turn? Well, it is the tangential speed squared divided by the radius of curvature. This is how you calculate a centripetal acceleration. So for this object traveling in a circle, it is accelerating. So, and please pay very close attention to this part. This object traveling in a circle is accelerating, so we know that it is governed under Newton's second law. It has to be because it's accelerating. So any object that changes direction has to be obeying Newton's second law, except that in this case, Newton's second law is about a different kind of acceleration. So if we know the object's traveling in a circular path, it's a centripetal acceleration that's causing it. This part here, the unbalanced force, there has to be something that causes this change. There is no centripetal force. I'm not adding a list of forces to your list of things, but there has to be an unbalanced force that causes a centripetal acceleration. For the stopper, it was tension. The tension caused it. For your car making a turn, it's friction. Friction pushes onto tires. For you making a turn going out into the hall, it's friction between your shoes and floor. There has to be an external force acting on your object to cause it to change direction, but it's going to be something out of your list. Does everybody understand what I'm trying to say? They don't have these much anymore, but let's see if you know what I'm talking about here. It's hard to find a one of these, but I'll do my best to see if you know what they are. Kind of looks like this, but I'm going to do my best to make it look like something you've seen before. Let's see, I want that, and I want that. So, does this look like something you remember? Anybody seen one of these? They, you and a bunch of your friends get there, and your friends kind of line up around here, and you spin the thing, and then somebody comes running and jumps on it. Now you know what I'm talking about? Has anybody seen a merry-go-round before? They don't make them much, do they? They keep taking them out of parks because I don't. Well, there's a lot of reasons I assume. I mean, because it's hard to see it from the top down. Maybe I need a one of these to kind of help put it in perspective. Like from the side, it kind of looks like this, and those bars are like. Right? It's on like a spindle here, and then the ground is like here. Yeah, but they probably are tired of kids getting their head stuck there, and there's hypodermic needles out here and stuff. They don't want people to get stuck on the. I mean, that's what the problem is with parks is kids get hurt because mommy isn't paying very close attention, or daddy's watching a sports game, and then the kid gets hurt. So they take all these fun things out, but these were the best to have in there. I mean, I went to a park a couple months ago with a niece, and it was terrible. There was nothing there. Like, do you remember these? Let's see if I can draw it right.
Oh my gosh, these are so fun.
Oh,
The springy things, yeah. Right? Doing that thing? I went to a park with my niece, and I had those. They replaced the springs with posts. It was terrible. What kind of park is that? Of course, how many of you have been on one of these? Let's see. See if I can draw this okay.
Yeah, they keep like the metal slides that you shock yourself on.
Right, something like this. Anybody been on one of those? Where you kind of sit here and I sit here.
Oh my gosh.
And then I jump off right here, and then you go plummeting to your horrible demise, right? All these things are they're gone. Like they just don't have them at parks the same way they used to. But merry-go-rounds used to be the best. Does anybody know a park that has a merry-go-round still? Where?
There's one up.
Well, I'm thinking field trip, but I mean, they make the adult version of a merry-go-round. Have you guys been on one of these? Let's see if I can draw this one right. Looks kind of like this.
Oh my gosh. I've never been.
It's a one of these where you kind of stand around in a circle.
Oh, that's right. It's like hollow in the middle.
Right, and
Never been on one of those.
it's kind of looks like this. So you're here, your friends are all here, and it's on a platform. So that part way through when it's spinning, suddenly the whole thing does like a one of those while you're spinning. You guys been on one of those at the State Fair? So I want you to think about it for just a minute. If this is spinning like this, with a we call this an angular speed because the whole ride is spinning. So we use a lowercase omega for this. And just to keep this in mind, remember that we are still in class. Lowercase omega looks like that. It's like a W with a little flare. And it's, I'll say the word omega, but it stands for angular velocity. It represents how fast something's spinning. So all the people that are on this ride, they all have the same angular velocity because they're all part of the same thing and the whole thing's spinning at the same speed. You follow so far? So in this ride, what do you think causes the people to travel in a circle? I mean, at this instant, right now, when we're looking at them all, this person's going this way. That's their tangential velocity. Are they going to be going that way for very long? No, not if the ride is successful. If the ride's unsuccessful, they go this way. And that usually means the park shuts down for a little while as they investigate. But if the ride is successful, they will eventually be over here with a tangential speed this way. That's the goal. Something had to cause their speed to change direction. What causes their speed to change direction? That's right. If you think, we still have all the same forces that we've been talking about. The only thing that could possibly be pushing on them towards the center, based on our list of forces, would have to be a force in this direction. And the only thing that exists there is the normal force. The normal force will cause them to change direction. I'm reiterating this because I want to remind you, for an object to travel in a circular path, the only difference we're going to say is that the acceleration is going to be based on their speed and their radius of curvature. We're going to be making a substitution for their acceleration that we didn't do before, because we're not changing how fast they're going, we're changing what direction they're traveling. But on this side, the list of forces, well, that list of forces is always going to be something that's out of our list. Now, I like talking about amusement park rides, and we will, but I'll remind you that this unit is supposed to be about gravity. So let's talk about gravity for a minute, because it makes for a perfect exercise in circular motion. So imagine I have a spaceship. Here's my spaceship. Tell me how awesome my spaceship looks.
It looks so cool.
Okay, thank you for lying, appreciate it. It's my space fish. Okay. Now, in order for an object to be in orbit, you have to understand that there's a delicate balance that has to be struck. There's lots of different kinds of orbits. For today, we're going to talk about purely circular orbits. Anybody in astronomy? Nobody? Anybody taken astronomy before? So nobody's heard of Kepler's laws? Okay, good. So I can say anything I want now and you won't know the difference. Circular orbits are a subset of orbits. Most orbits aren't circular. Most orbits are elliptical. So we're going to talk about a special case and then we'll talk about the general case later. But circular orbits are things that we tend to use all the time for things that we put in orbit, like communication satellites, weather satellites, probably super secret military satellites. We put things in orbit all the time. The space station is in orbit. So calculating an orbit has a couple of qualities. First, it has to obey the rules of circular motion. So any object that's going to be in orbit has to have a centripetal acceleration. That means that its acceleration is based on the radius of curvature and how fast it's traveling. But also, in order to be in orbit, there must be an unbalanced force pulling that object towards the center. Well, what do you think that force is going to be?
Gravity.
Yeah, we just talked about it yesterday, the gravitational force. The reason we bring up circular motion when we talk about gravity is because it's the perfect time. Most objects that are in orbit are being acted on by gravity, and they have to obey this balance. So although just yesterday we were talking about, we're going to apply it to talk about what it means to be in orbit. An orbit is any time the gravitational force causes centripetal acceleration. That's what an orbit is. Anytime the gravitational force causes centripetal acceleration. There are some properties about orbits that you need to know, and most of them I think are obvious. First, all objects that are in orbit have some kind of tangential speed. They're going to have a gravitational force that is acting on them to keep them traveling in a circular path. And they will have to have a radius of curvature. That'll be the distance between the center of the object they're orbiting and the center of the object that is doing the orbiting. So in this case, it would be the center of the spaceship to the center of the planet. There's also another measure, this distance. The distance from the surface of the planet to the orbit, that's called the altitude. So if you're given an altitude, you may have to add it to the radius of the planet before you can use it. Does that make sense? So the orbital radius includes the altitude and the planet's radius. Now, the very first thing I want you to understand is that astronauts are experiencing gravity the whole time. It's what's holding the spaceship around the planet. So they are not weightless. They have weight. It's that they're falling the whole time. If you look clearly at what's happening, the spaceship is falling towards the Earth, but moving to the side all the time. So they're falling the whole time, which is why they look weightless, because their spaceship is falling. It just happens to be moving sideways fast enough to not crash into the Earth. If you want to bring your astronaut back, it's really simple. You slow them down. Try it. If you slow them down and you reduce the velocity, this balance is off. The top V changes, but if F doesn't change, they start crashing to the ground. Of course, there's the other side of that. If you want to get them to leave, like never see them again, well, then you do the opposite. You make the velocity really, really big, and they're traveling too fast now to stay around the planet, and they leave. Now, the truth is, it's really hard to leave the Earth. It takes a lot of velocity, a lot of energy. Most things can't leave the Earth. That's why getting something into just orbit is hard to do. Every time you hear about us launching a space probe to another planet, that takes an incredible amount of energy and ingenuity. We usually don't have enough fuel to actually do it. We have to shoot it like towards the sun and slingshot it around the sun or something like that to give it more energy, because it's hard to get to the kind of speeds necessary to leave the Earth. Now, I need you to be able to calculate orbits. And the properties I need you to calculate are things like how long does it take an object to travel around in a circle, or how fast must it be going to be in orbit. We're going to do an example right now, and you have all of the things that you need from yesterday to do this. You have the mass of the Earth, which is 5.97 times 10 to the 24th kilograms. You have the radius of the Earth, which, although I gave it wrong at first, I got it right later, 3.67 times 10 to the 6 meters. 6.37 times 10 to the 6 meters. Did I not say that? Oh. It's 6.37 times 10 to the 6 meters. And what I want you to calculate, just pretty straightforward, is how fast would the space shuttle have to be traveling to be in orbit? Now, what you want from me is the altitude, how high above the Earth. But believe it or not, the space shuttle was so close to the surface of the Earth that I could give you the altitude. It won't change these numbers because it wasn't that high. So unless I go out a few more decimal places, just use that number. That's how close the space shuttle was when it's first launched in its initial orbit. It goes higher when it goes to the space station, but not by much. What we'll actually find here is going to be how long it takes the space station to go around the Earth. We'll be off by a couple of seconds. That's it. Okay? So, first thing I want you to do, I want you to figure out how fast we have to get the space shuttle going to get it in orbit. That's our first calculation. I'm going to show you how to do it. You ready to go? All right. First, this M right here is the object doing the orbiting. So So I want you to label that in your notes that this is what is orbiting. So this would be the mass of the spaceship because it's doing the orbiting. The Earth is also experiencing a force, but we really don't say that the Earth is in orbit around the spaceship. We say the spaceship is in orbit around the Earth because it's the spaceship that's really affected by the Earth's gravity. The Earth isn't affected that much. So I'm going to bring up my force of gravity equation, which is mass of planet, mass of spaceship, g, divided by the separation distance squared. And that's going to equal the mass of the spaceship, the thing that is orbiting, times the velocity of the spaceship divided by the radius of curvature. Now you'll notice right now, because I'm trying to teach this to you, I've kind of made the r's different. Okay, so here's the thing you have to ask yourself before you can do this problem. Is the radius of curvature the separation distance? You should ask that question. In most cases, for our class, they will be the same thing. For most cases in our class, they'll be the same thing, but not in all cases. For example, the Earth and Moon, they wouldn't be the same thing. Because the Moon is really big, they actually orbit about a point in the middle somewhere. That's why the Earth wobbles and why we have tides. So for a spaceship, which really doesn't cause the Earth to move very much, they're the same thing. And because they are, I'm going to write them as the same thing. But you have to ask that question. It's an important question I need you to ask. Because you need to be cognizant that this only works if the object that's orbiting is very small compared to the thing that's being orbited. That's the condition. Is the thing that's doing the orbiting very small compared to the planet you're orbiting? All right. Once you've done this, I hope you realize that the thing that's doing the orbiting, its mass doesn't matter. So if you're looking for qualitative information, everything orbits at the same speed, at the same altitude. Everything orbits at the same speed, at the same altitude. The mass cancels out. It's never about the thing that's orbiting. So whether I want to put a rock of space P or a spaceship at this location, they have to have the same speed. That means that everything that's in orbit at that same speed, or at the same altitude, is going the same speed. That's why it's hard to orchestrate, and that's why they talk about all the space debris that's out there. Once there's space debris out there, it's all going this fast. And just because we have our spaceship going this way doesn't mean there can't be something over here going this way. It's not like all the countries agree upon what direction you have to orbit. There are reasons why we go in one direction versus another, but there's also people going this way, right? There's lots of different possible orbits. We've had collisions out there, and collisions are spectacular. It spreads space debris for hundreds of thousands of miles. So, first thing first, we cancel out the object that's orbiting. Its mass goes away. Next, you'll notice we can cancel out one of the r's. Right, there's an r on both sides. So what you're left with is mass of planet times g over r equals v squared. Now, I would not commit this to memory. It's not worth it because it's too easy to derive. But this would be the required velocity to be in orbit at the altitude that is just above the atmosphere. So you have your fancy calculators. Figure out this speed. We should all get the same number. Nemo?
No, I do.
All right, so again, this is how fast the space shuttle goes. We're just trying to figure out how fast we're going on the surface of the Earth. Installing what?
I just, good notes.
Oh, wait, is it actually just that?
Come on, folks. We're just spinning like that, right? That's what we just talked about. You're a point on the edge. We're trying to figure out how fast you're going because the Earth is spinning. And we know that it makes one circumference every 24 hours. This is how we calculate velocity, for something that's spinning like this. It's a way to do it, right? So you'll need to figure out 24 hours as seconds to do this. So every 24 hours times 60 times 60.
You can do 2 pi or 2.
You'll need the pi in there. into one place. We've talked about the force of gravity. You've talked about the fact that it can be used to figure out an orbit by setting it equal to the centripetal acceleration. So this is centripetal motion. You said if you combine them, you can use it to figure out the speed of something in orbit. And lastly, you can do more than that. We didn't get this far, but you should be able to use this plus this to figure out how long it takes something to orbit. For example, we just found that it's 7,900 meters per second for the shuttle to go in orbit, to be in a low orbit. You should be able to figure out how long it takes to orbit. By tomorrow, please, try this. Did you say, what is it on the sun?
On Saturn.
I don't know, Saturn doesn't have a surface, so that'd be hard to do.
That's gas.
So you can't really stand on it. Same with Jupiter. It's just it's a more and more dense. It's
So the rings around